Monomers are a single unit of a molecule. Polymers are simply a chain of monomers that are bonded together through the process of polymerization. In this video, addition polymerization will be explained through the use of two types of polymers, low-density polyethylene and polyvinyl chloride, also known as PVC, and the ways in which these properties relate to their uses. So let's begin with polyethylene. Polyethylene is one of the most commonly used polymers in the world. It's used in many materials and equipment for day-to-day life as well as industry purposes. There are two main types of polyethylene: low-density polyethylene, LDPE, and high-density polyethylene, which is HDPE. However, in this video today, it will only look at low-density polyethylene. Polyethylene is a type of polymer which is formed through the addition polymerization of the monomer ethylene. Addition polymerization is the formation of a polymer by the bonding together of monomers without the loss of atoms. This then forms ethylene, which is the monomer for the polymer polyethylene and has the molecular formula of C2H4. This is a monomer, and more specifically the monomer ethylene. It has 2 carbons and 4 hydrogens with a carbon-to-carbon double. This is from the base ethene. Following this, the addition polymerization reaction occurs. There are 3 steps involved in this process. Step 1 is the chain initiation step. This is where an initiator is added to the monomer to cause the reaction to begin. The initiator in this case is a free radical from the breaking of the molecule hydrogen peroxide. Due to the oxygen-to-oxygen single bond, the molecule is able to become a free radical spontaneously breaking apart by very little amount of energy, such as UV light. After the bond is broken, it creates 2 free radicals in the form of OH, which is unbonded electrons. For this model, we'll be just looking at one of them. It has the oxygen and the hydrogen. In this model, we'll be looking at the pointy end as the free radical that is the unbonded electron. This free radical is very electronegative, and due to the double bond of the monomer having many electrons surrounding it, the free radical is attracted to the ethylene. It attacks the double carbon-to-carbon bond of the ethylene, breaking and opening the double bond. Half the double bond joins the oxygen bond, which results in the other carbon that was originally part of the bond in being left with an unbonded electron, which this then becomes the free radical. This free radical of the molecule is now urgent to bond with another molecule, in which it is attracted to the double bond of the ethylene, continuing this process. This then begins step 2, chain propagation. The monomers add onto the chain. With each new monomer, it creates a place for the next monomer to be attached. As the free radicals are urgent to bond, they will bond in any random order, which can cause a branch to form. This is essentially how the low-density polyethylene gets its branch shape. Here we see a long, branched, low-density chain that has formed through the process of polymerization. This will continue to propagate until step 3, which is chain termination. This is where the 2 free radicals attract one another and combine, which in turn completes the polyethylene. This results in the polymerization process being terminated. As we can see from this model, there is 2 long branched chain low-density polyethylenes, which both have free radicals on their carbons. So as they go to attract each other, they combine, and this terminates the process of polymerization. The properties of the polymers are dependent on the structure of the molecules and their bond. Polyethylene is classified as thermoplastic, which means that it softens on heating and is able to be recycled. Due to its production process, where the free radicals are urgently wanting to bond with another electron, they attach at random places, which causes a branch structure. This is known as an amorphous structure. As seen in this model, there are many different polyethylene chains that are trying to be put together closely. However, due to the branches, this is not possible in comparison to a crystalline structure, one of a linear chain. This amorphous structure is branched, meaning that the molecules are further apart and that this molecule is not able to be packed closely together. This decreases the strength of the intermolecular forces, which are dispersion forces, and this results in a lower density and it's soft to touch. This means that it is much easier for the bonds to be broken than in high-density polyethylene. Due to the weaker dispersion forces this polymer has, a lower melting boiling point, and is high in flexibility. Again, due to the large gaps between the molecules, it means that the low-density polyethylene is transparent. You can see this aspect through this model, as you are able to see the blue paper underneath the polyethylene model because of all the gaps. Again, this is the same in real life as the polyethylene is transparent and therefore see-through. Due to the properties, as explained, it is evident to see how it benefits its uses. Low-density polyethylene is used in plastic bags, soft toys, plastic food wraps, and many other materials. All these materials have low density, are flexible in their structure, transparent in color, and are able to be heated to change its structure. The structure and in turn the properties of this polymer can be changed if the side groups of the carbon backbone are changed. For example, if a hydrogen was replaced with a chlorine atom, this would create the polymer polyvinyl chloride, which will be explored next. Okay, let's talk about polyvinyl chloride. Polyvinyl chloride is a type of polymer which is similar to polyethylene. It is a very common polymer, one many people know, especially by the name of PVC. The monomer of polyvinyl chloride is vinyl chloride, which has the chemical formula C2H3Cl. The only difference between this one and the polyethylene is that one of the hydrogens is replaced with a chlorine atom, and then this is further polymerized to become polyvinyl chloride. The polymerization process is the same as the polyethylene process, in which it undergoes initiation, propagation, and is then terminated. The only difference is the structure, as one of the hydrogen atoms have changed. This polymer is mainly amorphous, which is due to the way in which the chlorine atoms stick out of the chain, which is a result of the larger size of the chlorine. Although it has this type of structure, it has differing properties. PVC is hard and rigid, which is unusual for the amorphous structure, which are usually flexible and soft due to their low density. However, this is explained as a result of the chlorine to carbon bonds. Chlorine is highly electronegative, meaning that when bonded with the carbon, it creates a polar bond and becomes slightly negatively charged, and the carbon atoms become slightly positively charged. This creates dipole-dipole forces, which are stronger than those of the carbon to hydrogen bonds, which are only dispersion forces. This means that the intermolecular forces are stronger, being able to hold the polymer tightly, giving it the unusual properties that it does have. In saying this though, the properties of the PVC are able to be changed if additives are placed in between the chains. For example, PVC is able to become more flexible in its manner when plasticizers, which are small molecules, are inserted between the polymer chains, which hold the chains further apart, which weaken the forces. Additives can also change the color of the PVC, so it can be colored or remain transparent. A physical model was created for this video to illustrate the polymers and the production process they go through for them to be created. It also shows the structure of the polymers and makes the connection of how the structure impacts the properties of the polymers. So firstly, looking at the benefits, the model uses different colours and shapes to represent the atoms, and this is a useful and easy way to identify the different atoms and comparing the different atoms from the PVC to the LDPE. This is an eye-catching way and an easy way just to explain how the atoms are different and then how they may change and move around. Another aspect is how well it represents the properties. So due to the model showing the branches and the big gaps, you can really easily see how this would relate to real life in the transparency, as you're able to see the blue paper, the low density due to lots of the branches. It gives you a real visual of what this is like in real life. And then lastly, this model is very simple, and this does have positives and negatives to this. The simplicity of this model gives an overall understanding of the polymers in an easy and simplistic way. This shows how it's produced, the structure, how the structure affects the properties, and then how these properties are used in materials and equipment for everyday life. This is really easy and helpful for new people to come and learn a little bit more about polymers. There are, however, limitations to this model. One in particular being that it's not to scale. This obviously is not possible to do, but it is a limitation that we are not able to get the real small size of the atoms and the bonds. Another aspect is that with the use of the toothpicks and the skewers that represent the bonds between the atoms, it doesn't give a realistic representation of the actual structure of the backbone, which can be curved and isn't always straight. So whereas in this model it illustrates that the bonds are linear. The last thing that really does limit this model is that it cannot accurately represent the actual movement of the atoms which join the bonds and show the bonds that are splitting. In that sense, it doesn't give you a real accurate representation of that you aren't able to see how in particular they split and then how they move around and they go to join. But in saying that, it does give a pretty simple, easy way of understanding just how they do move without going into too much detail. So making an overall judgment, although this model doesn't go into complete detail about each of the things, it does give an overall process of the production of these two polymers and shows the way in which the properties are dependent on the structure and then how these properties are used in our everyday lives. So overall, I think it does a pretty good job in that. However, it is noted that it does have limitations.